Hi guys, welcome back. So today after the lecture, I think Ehsan is having a review session. So I'm glad to see so many of you guys here. That's always a good sign. They're not here for me, they're here for you. Okay, so we're gonna have about 3 lectures. I want to teach you about classification using various approaches. So today we're gonna begin with regression, sort of the simplest way to do classification. We'll see the problems with regression. Fisher discriminant analysis, which is a determinist. Basically, it's a frequentist way to do a classification. Then we'll begin with the Bayes approach to classification, which we saw a little bit on Thursday. And based on what we did on Thursday, we'll do a little bit of analysis on what happens if our probabilities have different variances. So you'll see decision boundaries that are not simple classifiers of one or the other. You can have multiple decision boundaries. And then I'll talk about Chernoff's error bounds. You learn a little bit about how to analytically write minimum of two numbers using a power representation. And then that'll give us Chernoff's error bounds for Bayes classifiers. So we're going to begin with regression. So our problem today is classification. And I'm going to call it classification 1 because we're going to have 3 lectures on classification. So we'll begin with the easiest part. So I'm going to start with the problem by using regression. So what's wrong if we want to use regression to do classification? So we have some data. X is a vector, Y is a class that we have. Where, Y of I is, say we have 2 classes, 0 and 1. And we have some vector of data, y, going from y1 to yn. And we have some w, which represents our weight that we're going to be learning, w0 to wp. And we have our model where we have y hat is w transpose x, these vectors. And so we make our matrix X to look like this. And we then find our maximum likelihood estimate of this weight, which was the normal equation that you've seen before. All right. So what are we doing here? What are we finding? Let me give you an example of this. So suppose that X belongs to, we say, class 0 if my Y hat is less than or equal to 0.5, and we say X belongs to class 1 if my estimate says I have something bigger than 0.5. So we have some space of x1 and x2, let's say. So this is x1, this is x2, and we've sampled our data, and here's what we have. So I'm going to draw circles when it's one class. And I'm going to draw points when it's the other class. All right, so this was your data. And so, these circles here meant that that was class, say, 0. These dots meant that that data means that it belongs to class 1. You solve for W, you find the weight that, that gives you a model. And now what we're going to do is to use this to plot the classifier. So you're going to find that you're going to see a line that looks like this, where this line is equal to the following. 0.5 is equal to W0 plus W1, X1 plus W2, X2. That's your classifier that you found, which means 0.5 is W maximum likelihood transpose X. So this is fine. So you found a classifier that says these guys are going to be one class, these guys are going to be another class, and here's the equation for this classifier. So the problem with using regression is the following. Suppose that we had data that looked like this. So we have a few points that belong to one of these classes, and then a whole bunch of points that belong to this other class. So you go and find your maximum likelihood estimate, and maybe it gives you this line. That's the line that you find. So this is the line that says 0.5 is equal to W transpose ML times X. Well, there's also going to exist this other line here, where here you have 1 equal to W transpose MLX. Basically what this means is that the weights that you're going to find are going to also give you some numbers that are more than any class that you have. So you're going to have things that are less than 0.5, you're going to say that's one class, you're going to have things between 0.5 and 1, and then you're going to have also some other points that are going to fall outside. So that's weird, because we only wanted to have something that was either one class or another class. So what's this? What's happening up here? So the problem is that what we have is that the distribution of the errors that we have are not normal, and so this is the problem that we have in the classifier that we made. So let me describe to you what was wrong with the way we set up our problem. So I want to show you that my prediction errors, which is basically my noise model, is not Gaussian in the classification problem. So let me show you what this means. So when we do linear regression, what we are assuming is that the data that we are seeing was generated by something that looks like this. There's a true W star that generates my data Y, but when I observe that data Y, I have the truth plus some noise, epsilon, where epsilon is normally distributed with some mean and some variance. The problem is that the data for a classification problem is not going to be consistent with this approach. So the problem is that if I look at the variance of Y given X, in this case, excuse me, that variance is of course just sigma squared. But now I'm going to show you that for classification, that variance is not going to be independent of the input X. That the input X in the classification problem is also going to influence the variance of your observation. So this model is inconsistent with the problem of classification. Let me show you why. So in classification, you have some probability of some class. Say C is equal to 1 given X, and say that's theta. And so you have the probability of the other class is 1 minus theta. So if that's the issue, if that's the probabilities of these classes, then the expected value of your class given the input X that you got is going to be, well, you have two classes, value 0 and value 1. Value 0 times its probability, 1 minus theta, plus value when it's 1 times its probability, which is theta, which is just theta. So expected value of C given X is theta. The expected value of quantity C squared given X, so I'm going to do this because I'm going to want to find the variance of my estimate. So that's 0 squared times 1 minus theta plus 1 squared times theta, that's also theta. So the variance of my class given X is the expected value of C squared given X minus the expected value of C given X quantity squared, which is then theta times 1 minus theta, which is equal to the probability that C is equal to 1 given X times the probability C is equal to 0 given X. Okay, so the point is that the variance is not independent of the input x, unlike regression. So this is why using regression to do classification gets you in trouble. So we want to use something else. And I'm going to go over some approaches to do classification that's consistent with the noise patterns of our problem. Before I go, let me ask you, do you have any questions so far? So you can always use regression to classify things, right? You can just say that if it's more than this number, I'm going to represent it be this class. Less than this number, I'm going to represent the other class. The problems with it is that the noise model for classification is not going to be appropriate for the noise model that you use for regression. So we need something better. So the first approach was was work that Fisher did. And Fisher is a famous guy in statistics. He did lots of work on finding p-values and so forth, and it's called Fisher discriminant analysis. And the basic idea is as follows. So you have some data that belongs to some class, and then you have some data that belongs to some other class. And what this problem is to find an axis. I'm going to draw it with a dashed line here. That if you were to project your data onto that axis and you look at the distribution of the data, so here's the data that belongs to one class, here's the data that belongs to another class. If you were to find this line, this axis here, upon which you're going to project your data, after you projected it, the means of the distributions that you get are as far apart as possible. So what Fisher discriminant analysis does is to find a coordinate system that when you project your data onto it, and of course projection is just a dot product, right? When you project your data onto that axis, and then you look at the distribution of your data projected onto that axis, you get them as far apart as possible. So if I had the same data as before, and I had picked another axis, say I had picked this axis, and I had looked at the distribution of my data. So here's my distribution. So the distances between these two means are less than this distance. So this is a better choice. And what this discriminant analysis does is to find a line that when you project your data onto it, it maximizes the distance between the projections. That's what we want to do. So we want to describe a cost function that is something to do with the projection of our data onto this axis, and then find the axis that does it best. Now, the math is a little bit interesting because until now, when we've been doing optimization, we find that we can find derivatives of our cost function with respect to the parameter that we're looking for, and then set that derivative equal to 0 and find the optimal parameter. In this case, we won't be able to find the derivative with respect to what we're looking for because it's a complicated cost function. But there's a nice geometric solution to the problem that will help us find it. And so this was the nice work that Fisher did that I want to show you guys. So our problem is that we have x and we have to classify it as either belonging to class C0 or C1. So here y is equal to 0, we're going to say here y is equal to 1. So when we have class 0, we have in that class we have n sub 0 data points. They have a mean mu 0 and they have a variance covariance matrix of sigma 0. I'll show you guys how we can define these guys. And then we have another class, y1, where I have n1 data points, where its mean is mu1 and its variance covariance is sigma 1. So what's important is that, as before, our data are labeled. So we're building a model based on labeled data, right? So a teacher is there that tells us this data belongs to class 1, this data belongs to class 0. Well, how many data points do you have in each class? N0 and N1. What's the mean of each class? What's the variance of each class? All right. So, obviously the mean, mu0, is 1 over n n0 sum over xi belong to class 0 of xi. That's the data points that you have. And the variance of x such that x belongs to class 0 is sigma 0, which is 1 over n0 times the sum of x of I minus mu0 x of I minus mu0 transpose. So these are estimates of the variance and covariance matrices. Over the data sets. Okay, any questions so far? We just defined the mean and variances of our each class. Yeah.
How we can be sure that the line that we share based on this method, we find that maximize distance between the means will be the best line, because it may increase the variance of the data in that projection.
Yeah, so it not only maximizes the distance, it normalizes it by the variance. So it's a little bit more sophisticated than just the distance. Good point. I'll show it to you how he does it. So my estimate of y hat, the class that it's going to belong to, is going to be W transpose X plus W0. What I want to know is what's W and W0. So you see, he's using regression, right? He's using regression to find the classifier. The Fisher discriminant analysis is based on regression to find the classifier. So he's going to have the problems that I mentioned to you before. But nevertheless, I want to show you what he did. Okay, so then, the expected value of y hat, given that x belongs to class 0, is, of course, W transpose times expected value of x, given that it belongs to class 0, plus W0, which is just W transpose mu0 plus W0. And the variance of my estimate, given that x belongs to class 0, is W transpose sigma 0 W. Okay, so here's the cost function that he says would be worthwhile to try to maximize in this case. He says take the distance, the separation of the two classes, square it, and divide it by the sum of the within class variance. So what this means is that take mu0 transpose W, the mean of the first class, minus mu of the mean of the second class, projected onto this W, which is that axis that we're going after. We want to know what this axis should be. The distance between the means divided by the sum of the within subject variance. Yeah.
Shouldn't it be W sigma transpose W transpose because it's a matrix?
No, in this case, Y, our observation, our class is just a scalar. So either one or the other. Either one class or the other. Okay, so what we want to do is find W that maximizes J. That's the Fisher discriminant, which is W is going to be a set of weights, basically, which is going to tell us what this line is supposed to be. That when we project our X onto, it will maximize the distance between the means, normalized by the within class variance. So, okay, so what we need to do is to maximize the following quantity. So I'm going to give some intermediate variables for us to consider. Let's call this M. Let's call this S. So M is the differences in the means. S is the weighted variances of my system. So this is equal to M transpose W squared divided by W transpose SW. So we want to find the W that maximizes this quantity. All right. So how are we going to do it? Well, what we can do is to take our matrix S, which is the sum of two covariance matrices, and represent it as what's called a square root matrix, which is R transpose R. R is going to be what's called the square root matrix of S. So S we know, we can define this thing called R transpose R, and I'm going to also define a vector V, which I'm going to write as RW. And you'll see why this is going to make our life a little bit easier. So if this is the case, then W is R minus 1V. So let me rewrite J now, not in terms of W, but in terms of V, which I'm going to have M transpose, W is R minus 1V, quantity squared, and my denominator now is going to become W transpose is V transpose, R minus 1 transpose, times S, which is R transpose R, times W, which is R minus 1V. So my denominator became much simpler. Now I have M transpose R minus 1V in the numerator squared, and in the denominator I have V transpose V. Okay, so this I can further simplify. This is this quantity here, M transpose R minus 1. I can write it as R minus 1 transpose M quantity transpose V quantity squared divided by V transpose V. And of course V transpose V, what is this? This is just the square root of V transpose V quantity squared. So I'm going to be able to take this, put it inside of the squared quantity. So I'm going to get J of V is equal to R minus 1 transpose times M quantity transpose times the vector V divided by its length, quantity squared. So this quantity, which is in terms of V, is maximized when this vector r minus Tm is parallel to the unit vector V divided by its size, divided by its norm. So that means that V should be a scalar, arbitrary scalar, A times R minus 1 transpose times M. And which was, what was R? R was the variance-covariance matrix, the square root of it. Okay, so, which is what? Which is this is equal to some constant R times R minus 1 transpose times mu 0 minus mu 1. And what was W? W was R minus 1 times V, which is equal to A, R minus 1 transpose mu 0 mu 1. W is equal to this arbitrary constant A, which is this term here is S minus 1. S minus 1 mu 0 minus mu 1. So W is the following. I'm going to drop this arbitrary constant, just set it equal to 1. I have S minus 1. S was N0, variance of the first class, plus N1, variance of the second class, inverse, times the means of the data. This weight maximizes the distance between the means of the data. So this, we have every element in here. We have the number of data points in class 0. We have the variance covariance of that class. We have the number of data points in class 1. We have the variance covariance of that class. We have the mean of the data in that class, and we have the mean of the data in the other class. This vector W gives you the line that you need to project your data onto to then maximize the distance between the classes. And the other thing that you need is W0, which is just the expected value of y minus W transpose of x, which is in this case WI. So your model had a vector W and scalar W0. Here's how you find it to maximize the distance between the two classes. This is called the Fisher discriminant analysis. It uses regression to optimize a cost that is defined as the projected distance between your data when it's projected onto the some coordinate system, with the goal of finding the coordinate system that maximizes the distance. Okay, any questions, guys? So the only interesting thing here, I think, something that you haven't seen before, is that how do we find a cost function? How do we find the parameters of a cost function that have this structure? A quadratic form divided by another quadratic form. And in this case, we can find the solution analytically using a geometric representation by change of variables, which I showed you here. All right. All right, let's go back to Bayes. Because with Bayes analysis, we don't need to worry about the problem that we have in describing the probability of the noise and how that noise is going to be in classification dependent on the input that I had, x's that I had. So I will briefly review what we've done a little bit on Bayes classifier and try to extend it a little bit for our discussion today. So Bayes classifier. I'm going to begin with what we did on Thursday, which was that we have equal variance. in the two classes. All right, so we begin with the likelihood of our data. We have some data X that C, when it was class, one of the classes, we say that's normally distributed with some mean mu 0 and variance sigma squared. And we also have the other class, when it's class 1. It's also normally distributed with mean mu 1 and variance sigma squared. So the two likelihoods have the same variance. So what does this mean? So when I have some input X, say the height of the individual, we have some distribution when it is class 0, and I have another distribution when it is class 1. All right, so to find our posterior probability, we need the likelihood, we need the prior, we need the marginal. So let's begin with the marginal. What's P of X? Well, that's P of X given that class is 0 times the prior probability of class 0 plus the probability of class 1 times the prior probability of class 1. That's our marginal. And then our posterior probability that we have class 0 given X, is the likelihood times the prior probability divided by the marginal. So all right, so here was our likelihoods. Suppose that our prior probabilities are equal, so I'm going to multiply these guys by the same prior probability. What's our marginal going to look like? Well, our marginal is the likelihood of one class times prior probability plus likelihood of the other class times the prior probability. So it's going to look something like this. This is what the marginal is going to look like. So now what I want is the posterior probability. So I take for each variable x, so I take each one of these guys, a number here, and I say, what's the likelihood, which here it is, times its prior probability divided by the marginal down here. So what am I going to get? It's going to look like this. So say that I'm interested in class 0, which is this class here. I'm going to get a probability that's going to look like this. This is going to be the posterior probability of class 0 given x. And then the posterior probability for the other one is going to look like this. Does that make sense? Okay, so this is called a decision boundary. This line that I drew, it says that things that are bigger than x here, I'm going to classify as class 0. Things that are smaller than this decision boundary, I'm going to put as class 0. Things that are bigger, I'm going to put as class 1. And so my decision boundary is as follows. Some x where probability of c is equal to 0 given x is equal to the probability of c is equal to 1 given x. So this x here happens to be the same at the location where the posterior probabilities are equal, and that's called the decision boundary. Where, of course, when the posterior probabilities are equal, what that means, that's the same place as the likelihood of x given c0 times the probability of prior probability of c0 is equal to the likelihood of x given C1 times the probability of C1. So then to classify, what I need is just the ratio of the two numerators. So what I really need is to understand whether the probability of x given class 0 times the prior probability with respect to the other class. So if this ratio is bigger than 1, then I say your data is class 0. Because I'm using the posterior probabilities to classify, and really what I want is the ratio of the two probabilities, which when I find the two ratios, the marginals go away. If that ratio is bigger than 1, then I have class 0. If it's less than 1, then I have class 1. Does that make sense? All right, let's do unequal variance. See what happens then. So what I have here now under unequal variance, I have my data x, I have some distribution, the likelihood of x given that I have class 0, and I have another distribution. And this is p of x given that the class is 1. So obviously the variances of the two distributions are different. So what's going to be my my marginal? Well, let's assume that my prior probabilities are the same, so my marginal is going to look something like with a long tail. All right, so now what about my posterior probabilities? Well, if you look at these places where the likelihoods cross, so I want to plot now the posterior probability. Say the posterior probability of class 1. So this was class 1, this guy here. That's going to look like this. The posterior probability for class 0 is going to look like this. So now I have two decision boundaries. I have one location where when I'm smaller than this, I'm going to say class 1. When I'm bigger than this, I'm going to say class 2. When I'm in between, I'm going to say class 0. Okay, so this gives me a way to use Bayes probability under the conditions that we've seen, equal variance, unequal variance, come up with the posterior probabilities and to form a decision boundary. And then in a couple of lectures, we'll see how to model these posterior probabilities, these functions themselves, as a function of the input x, and how we find what these functions are if we've been given some data, rather than, plotting it by hand or computing the likelihoods and dividing it. We can see that the function itself is an analytic function of the input x, and that's called logistic regression, and we'll get to that. Okay, but when we have such results, we can also describe errors that we're going to have. So, for example, look at this distribution here. So this likelihood here tells me class 1. This likelihood here gives me class 0. So basically, if I have data here, x's here, there's some probability that they belong to this distribution, class 0, but I'm going to classify them as class 1, right? So I'm going to misclassify it. Does that make sense? Similar out here. So out here, there's some probability that I have class 0, but I'm going to classify that as 1. So that's the errors in my classifier, right? And we can try to understand what these errors are and quantify them. So in general, you know, when you have two likelihoods, here's one likelihood, you know, here's the other likelihood. And here's your decision boundary, someplace here. Well, then the area here is going to be misclassified, and the area here is going to be misclassified as well. So this is probability of x given that you have class 0 times the prior probability of class 0. This is probability of x given that you have class 1 times the prior probability of class 1. So this here is data belongs to class C0, but will be misclassified as C1. And that area under that curve, which is P of x C0 times prior probability of C0 dx, where x goes from your boundary, I'm going to call that R0, to infinity, that area is what describes my probability of error. So my probability of error is this area plus the other area. So in principle, of course, these areas can be, you know, very complicated. You can have unequal variances, vector spaces for x, and places where they are discontinuous that you would have to integrate. And so a useful identity that I want to show you, a useful result, is called the Charnoff bound on the Bayes error rate. Which is basically for us to know when we classify things using Bayes probability, what's the bound on our error? And the idea is as follows. So you have two probability distributions here, right? You have one for class 1, one for class 0. And basically, the integral of the smaller probability distribution is your error. So you have two distributions, you have two functions. You want to integrate, these functions are positive. You want to integrate the smaller of the two functions over some range. And you want to know what is that integral going to look like. So here's what Charnoff did. So he said, in principle, when you want to find the minimum between two variables, A and B, that they have a special property, A and B are both bigger than 0, so they're probabilities, right? So they can't be negative. Then he said this minimum can be written as the following identity. A to a parameter beta, B to the parameter 1 minus beta. I want to explain to you where does this come from. So why? Why is this true? What's special about beta is that beta is bounded between 0 and 1. So there exists some beta. Sorry, for all beta between 0 and 1, this is true. this identity is true. I want to show you why that is. So let's simplify this a little bit. A beta times B 1 minus beta. What is that? Well, that's A beta B to the minus beta times B, which is equal to A over B to the quantity beta times B. Do you see that? Yeah? I haven't done anything, right? Just algebra so far. But we have to make sure we understand that A to the power beta times B to the power 1 minus beta is equal to the ratio of A to B raised to the power beta times B. All right. So our objective is to find the minimum between two numbers, A and B. And what Charnoff is saying is that minimum is bounded by this quantity. He says no matter what A and B are, as long as they're bigger than 0, the smaller of the two is bounded by this quantity. So why is that? So suppose B is less than A. So obviously if B is less than A, then the minimum of A and B is B. So if B is less than A, then A over B is greater than 1, right? Which means that B is less than A over B to the beta times B. So far so good. So if I want to find the minimum of A and B, if B is less than A, then minimum of A and B, which is B, it's less than this quantity, which is true. Here it is. I just showed it to you. On the other hand, if A is less than B, then A over B is less than 1. And so A is less than A over B raised to the power B times B. So again, this is true. So if A is less than B, then minimum of this is A, and A is less than this quantity, which is equal to this quantity. So in general, this is true. So minimum of A and B is less than or equal to A over B to the power beta times B, which means that this is less than or equal to A beta B 1 minus beta. All right, why is this useful for us? So we wanted to find the probability of error. So you wanted to find the probability of error. Let me show you how to do it. We have an integral of two minimums. We have an integral of a minimum, right? So remember, we had two probability densities. We had the likelihood of one distribution, we had likelihood of one class, likelihood of another class. We want to find the minimum of those two things and then integrate it. So that's the minimum of the first distribution, the probability of C is equal to 1 times x, the posterior probability, and the posterior probability of C is equal to 0, given x, minimum of this dx, which is equal to the minimum of the likelihoods, P of x given C is equal to 1 times the probability of C is equal to 1 P of x C is equal to 0 times probability of C is equal to 0. The minimum of this, we want to integrate it. That's our probability of error. Okay. So with that inequality that we had, that the minimum of A and B is less than or equal to A to the power beta B to the power of 1 minus beta, we can say that this integral is the following. P of x given C is equal to 1 is less than or equal to probability of c is equal to 1 beta times probability of x c is equal to 0, 1 minus beta times probability of c is equal to 0, 1 minus beta dx. So, look, we know the likelihood. We know the prior probability. We know these probabilities. And now what it's saying is that your probability of error is less than or equal to these things that you know raised to some power beta that you don't know, integrated over dx. And so what Charnoff said is, and so of course this is less than or equal to, these guys don't depend on x. I'm just going to bring it outside the integral. Probability of c is equal to 0, 1 minus beta. Probability of c is equal to 1 beta times the integral of the likelihoods. So what Charnoff said is that you can find the probabilities to find, after you do Bayes classification, to find your probability of error, find the beta that minimizes the above expression. Because this is a bound. And you know the prior probabilities, you know the likelihoods, and by finding a beta that minimizes this probability of error, which is what your Bayes classifier has done, your Bayes classifier has done this classification, your probability error is going to be bounded by this quantity, where beta is a quantity that minimizes the above expression. And that's called Charnoff's error bounds on the Bayes classifier. So you not only get how good your classifier is in terms of the probabilities that you have, but you also get an estimate on how likely it is that you're going to make errors with your classifier, your probability of error. Okay. All right, guys, we're done. Do you have any questions? So, a useful thing that we learned today is this expression. Under these conditions. Which is nice, because minimum is a difficult thing. When you have minimum of two numbers, it's difficult to write it algebraically. This gives us a way to write it algebraically. Okay. Good luck with your tests on Thursday. Bring your notes, and I hope everybody does very well. Ehsan, you going to take over now? I don't know if you want to.